Hello, welcome to Taxonomy Online Mathematics. Today we want to have a lesson on the topic set and operations on set. To kickstart, we will start with the definition. We will also talk about some various examples. Then finally we talk about the types of set. If you have not subscribed, please subscribe to the channel. Like, share, and comment your thoughts. Let's get started. Now, when we talk of set, we say set is a well-defined collection of objects or of distinct objects. So we can have definitely the group of objects which are well-defined, a class of students. So it's a well-defined collection. We can have even numbers. A set of even numbers, a set of days of the month is a distinct, meaning it doesn't involve different class of objects or different groups of objects. So in representation of set, we use capital letters. So A, B, C, D as capital. Then the elements of a set are represented using the small letter, the lowercase. Then, if you want to talk about an element belonging to a given set, the symbol, as you are seeing, is used in order to show that the element belongs to a set. So, this simply means belongs to, is an element of, or is a member of. So, if we say a set of days of the week, I can say that Monday is a member of what? The set days of the week. And if we have like January is not a days of the week, then we have to use the symbol but cross it over to mean that the element H is not a member of the set A. Alright. What are some of the examples of set? Examples of set are just the natural numbers. We can say a set of natural numbers or a set of counting numbers. A set of integers. We also have a set of rational numbers, set of real numbers, the set of positive integers, then the set of all whole numbers. These are various examples of set. Now, if you want to describe a set, how do we describe a set? For a start, we can say that set can be described in three main parts or ways. One could be listing the element. Normally, if you want to list the element of a set, the elements of a set are enclosed in a bracket, which are separated by a comma. Each element is separated from each other by a comma. It is enclosed, meaning begin with a bracket and end with a bracket. So we can see that, for example, the set of prime numbers from 13 to what? From 3 to 13. Then we have 3, 5, 7, 9, 11, and 13. Since they are enclosed, we call it what? A set. This is a definite set. Now, we can also say that a set can be described using the stating of their property. You state the property of the set, still enclosed in a bracket. So, even numbers less than 12. A set of even numbers less than 12. A set of days of the week. A set of counting numbers between 10 and 40. That will be just stating the property of the set. Then we can also describe a set using the set builder notation, whereby we have a set of X such that 2 is less or equal to what? X. Then we can also say that X is also less or equal to 14. This set will become less ambiguous if we know what the X stands for. So in this case, the X is what? An even number. So we can also have the same set whereby we will say 2 less than x less than 14, where x will be a prime number. So it means that instead of listing 2, 4, 6, 8, 10, we will start from where? 3, 5, 7. Because the x is being defined for us. Now, let's talk about types. What are the types of set? Types of set. We have one, the universal set. A set of all elements that are under discussion. If I want to talk about alphabet of the letters of the alphabet, then the set A to Z is the universal set. So if I point a set such as the consonant, a set of consonants, I know that I'll be taking it from this set. If I say a set of vowels, I'll be deriving it from this set. So this set becomes the universal set. Likewise, on the other hand, if I want to discuss a set of counting numbers, then I have to consider all numbers starting from 1 down to infinity. That is how we can describe a universal set. Then 2, finite set. From the beginning, when we were defining what a set is, describing them, we have examples of sets which the number of elements is being known. The number of elements, simply put, the last element of the set is known. So it is a set which contains a definite number of elements. Meaning, if I ask you to state the set of days of the week, I don't expect you to continue talking from morning to evening. I just need you to give me a definite answer. There are 7 days of the week. So after stating those 7 days, you are done. That is definite. It's a finite set. So the set Q, which is 1, 2, 3, 4, 5, 6, is finite because it has 6 elements, which we are aware of that there are 6 elements. I can indicate the last element. Then we have month of the year. We know we have 12 months. So after stating all the 12 months, January to December, there is no other element I can add to that set. So that makes it a finite set. Then the opposite of finite set is what? Infinite set. Meaning it's a set whose element cannot be listed. You cannot list definitely the element of a set of counting numbers. If I just say set of counting numbers, you start, if I give you a starting point, as from 1, you might not be able to finish even from morning to evening, because you can get to 1,000 in the evening, while some will get to 1 million in the same evening. So it means that there are infinite numbers that we can state. So we become infinite set. A set whose last element is not known. And we use 3 dots to indicate. The 3 dots at the back of 5 indicate that the numbers continues. Alright. Then we have empty set. The word itself explains itself. If you say something is empty, a set with no element is called empty set, or it's a null set. It doesn't have any element at all. Then it is which does not contain any element. It is denoted by the symbol phi. Sometimes phi is denoted by what? Enclosed bracket with no element. It means it is empty. It can be concluded that the number of elements in an empty set is what? 0. The number of elements is 0. Empty set is therefore an example of what? Finite set. I mean, we know that there is no element, so we cannot continue adding element. So for example, the set of counting numbers greater than 0 and less than 1 could be given by this set period notation, as in from 0 less than x, x is less than 1, is an empty set, because we cannot state any number between which is what? Greater than 0, but it is less than 1. There is no number if you are referring to real numbers. Alright. Then we have a unit set. Unit simply means 1. So any element that have one set, any set that have one element is what we refer to as what? A unit set. So it has only one element. Example, as we are seeing, a month of the year with a fewer days than what? 30. or fewer than 30 days. We know it's only February that have that. So the set of B of even prime numbers. 2 is an even number, 2 is a prime number. So the only even prime number we have is what? 2. So 2 become the only element. So that makes it what? A finite set. A unit set, sorry. Then from the above definition, we are talking about finite, knowing that we have exactly 2, 3, 4, 5 elements. So we can also call something a cardinal number of set. The number of elements in a set is cardinal. So the total number of elements in a set P is called the cardinal number of set P, which is denoted by NP, meaning the number of elements of P. So for example, the set A, as in X, such that X is a natural number which is less than what? 5. So these numbers are less than 5. 1, 2, 3, 4. So how many elements are there? There are 4 elements. So the cardinal number is what? 4. Set B as a set of elements in the word mathematics. So we know mathematics, they are letters. We can count the letters to form what? 8. So there are 8 elements of the set. But note that if you have a set that contains 5, that is an empty set. It is a set of empty sets. So that is not an empty set. It is becoming what? A unit set. Which is what? Only one element out of that set. That is 0. But the number of elements there is 0. Because the empty set itself is 0. But if you are referring to this, you will call this a unit set. Because it has what? One element, which is the empty set. Then let's talk about the pair of sets. We are still on the type of set, but there are some type of sets are based on a pair of sets. They are basically defined in terms of 2 sets. These are the equivalent set and equal set, or joint or disjoint set. As the word explains, equal. When a set are equal, it means they have the same number of elements and the same element. So 2 sets PQ are said to be equal if they contain the same element. So for example, if P is an element, if element of P is in Q and the element of Q are also in P, then we can say that the 2 sets are what? Equal. For example, the P is having the set of T, H, E. Then Q have E, T, H. Since they have the same element, written in ascending and descending order, rambled together, we still have the same element, the same number, which is 3, 3. So we call it equal set. Set A is equal to set B. Then on the other hand, equivalent set is said to be equivalent. 2 sets are said to be equivalent if they have the same cardinal number, meaning the number of elements are the same. So for example, we can have set P having MEN, set Q having 1, 2, 3. Even though we have a set P of letters of the alphabet, set Q on the counting numbers, we say they are equivalent because they have the same number. How many numbers? 3, 3, 3. 3 each. So that become equivalent set. So can you answer this question? As in agreeing to the assertion that all equal sets are equivalent, but not all equivalent sets are equal. Do you buy into that idea that all equal sets are equivalent? Yes. If they have a set 1, 2, 3 and 3, 2, 1, we can say that the number of elements is what? 3, 3. So we can say that they are equivalent. The same time they are equal. But the example we have above, MEN 1, 2, 3. The number is 3, 3, but the elements are different. So that cannot be equal set. It is only what? Equivalent. That is what it means. Then the type of set continue as in disjoint. Disjoint set. 2 sets that have no element in common. So 2 sets are said to be disjoint if they do not have any element in common. If their elements are different, then we call it disjoint set. For example, a set A is a set of prime numbers. A set B is a set of composite numbers. Prime number have only two elements. Composites here have more than two elements. So there is no way we can be able to have those two sets having elements in common. Okay, so intersection of the two sets become what? Empty. Become a null set because there is no element in common. Which we can represent that on a pictorial diagram as this. So the two sets are not going to have overlapping. So the elements are going to be separately categorized on each set with no overlapping. That is what we call disjoint set. Then subset. As the word sub means part. So part of a set. So set A is said to be subset of another set B if all the elements of set A can be found in set B. If all the elements, it is not all cases. If you see that all the elements of set A are in set B and all the elements in set B are in set A, we call it a proper subset. But in this case, I'm referring to if I have counting numbers 1, 2, 3, as we are seeing for set P, 1, 2, 3, 4, 5, 6. Then the set Q, 1, 2, 3. Then Q is going to be a subset of P because the element of Q is derived from the element of P. So the symbol, as we are seeing, is being used to mean is a subset of. So from here, we can say that Q is a subset of what? P. Just look at the direction how the symbol is open. It is open to Q. And this is going to say the word Q is a subset of what? P. It means this is inside the P. Then this also means that Q is still Q is a subset of what? P. Meaning Q is inside what? P. So every set is a subset of itself, and an empty set is also a subset of every set. Since empty set is a set that have no element, I said earlier on that we call something proper subset. So if I have a set 1, 2, 3, that is set A, set B, 1, 2, 3, and I'm saying that A is a subset of B, and the element of B are exact element of A, then we can say that what? A is a proper subset. That's why we are saying that every set is a subset of itself. Then we have what we call power of set, meaning how many subsets can I derive from a given set. If I have a set of 1, 2, 3, how many different family of sets can I derive or take or reconstruct from that set? So if A is a set, then the collection or the family of all sets, that is subset of A, is what we call the power of set A, which is denoted by PA. Thus, if A is a set of I and S, that is I and S, then the power of A is going to be the set of I, the set of is, the set itself I and S, then the empty set. So it becomes 4 sets. So if I want to know how many subsets I can derive from a given set, then I use the symbol 2 exponent n, where n stand in for what? The number of what? Element in the set. So these are the various type of sets. We know we have what we call complement of a set, we have the union of a set, we have intersection of a set. I will deal with that in the next episode. We will take the remaining 3 type of sets, then marry it with the properties of set so that we can be able to do more working. I know this is more or less like reading. Workings will begin with that. If you find this video useful, please like, comment, share, and subscribe if you have not subscribed. If you have any reservation, if you have any other way which we can all learn together, hit me up in the comment section so that we get interactive. Thank you for watching. See you in the next episode.